This is a continuation of my monet transformer tutorial that I started recording about 2 years ago. The reason that there is a 2-year pause is that I found that there's far too much material that I have to carefully go through before I can continue recording the monet transformer tutorial. The material turned out to be very challenging from the technical perspective. So instead of continuing to record the slides, I decided I will write up all the derivations. Then I realized I should really start writing up the entire book because then I will know how to correctly explain and in what order to explain the derivations. And so I stopped recording tutorials and started writing up the material in those tutorials into the book. So the book is now close to being finished, although I have relatively little time to work on it now. I will try to continue where I left off in the first part of the monet transformer tutorial, using the book, going through the material that I have in chapter 14. Chapter 14 is ready. It's by far the longest chapter in the entire book and the most technically difficult. In the tutorial that I recorded 2 years ago, I stopped at the point of explaining the composed inside transformers. The composed inside transformers, or linear monads, as you might call them, is quite a limited class of monads. It contains basically just writer and option or either monads. I realized that before talking about composed inside transformers, it is useful to derive certain properties that are common between composed inside and composed outside transformers. These transformers both have the form of composition of type constructors. And the transformer is based on the swap function, the function that swaps the order of the functor type constructors. I found that I could derive common properties and so simplify the proofs, make them much shorter for the transformers of these two types. And so that's why I stopped writing up and stopped recording the tutorials and started writing up the derivations. And as I was writing them up, I found that there's far more material that needs to be covered, even in the practical section and in the laws section. And so essentially, I should really start this tutorial from the beginning. So let me therefore go through very quickly the chapter 14 of the book. I will not go through the derivations. I will just indicate what is being done and why. So this is kind of an overview of chapter 14. Instead of recording a monet transformer tutorial by slides as I was planning to. Now, to remind us why we need monet transformers, the reason is that we need to combine computations in a functor block with different monads. We cannot combine them directly. So for example, if you wanted to combine future and option, you cannot write code like this. This does not work. And the reason this does not work is that the type of the source must be the same or compatible throughout the entire functor block. So these type constructors must be the same, and they're not the same. The solution is to create a new type constructor that will describe both the effects of the monad future and option. So there will be a big monad to which we will convert these two values. So then the result will be something like this. But this, of course, also doesn't work because you are not so well, because you're supposed to define a flat map that operates on the argument inside future option, but you have not written that. So in this code, that's what we would like to do maybe, but this does not work. So we need to implement the flat map operation with respect to the type parameter A inside here. And so we can do that, and then we can define conversion functions or lift functions from future to this new type future option, which is just a wrapper over this. We define lifts from future to future option, from option to future option. Let's call these lifts by the word up. The name up is just a short name instead of writing lift, because lift is already defined on an option in the Scala library. So let's just say we define this up method as an extension method, and then we can write code like this. So this is good, it's reasonably short, and we hope to do this with any monads. But how do we combine two monads? So here we combined by composition. We composed future with option. But this does not always work. And then I show that this does not work with reader inside of either. And then I show different examples where it works and it doesn't work. So for example, you can compose future with either only in one way, and the other way doesn't work. Future with state, you just cannot compose in either way. State with reader, you can only compose in this way. And so on. So I show that in quite a few cases, only one order of composition works, and in some cases, neither of them works, like for example here. And so the question is then, how do you find the type that combines two monads? So the monad transformers is one approach that allows you to do that. In this approach, the idea is to fix the first monad, which will be called the base monad, and then let the second monad, M, be arbitrary. So we will write code which will only work for a fixed base monad, but it will work for an arbitrary second monad, which we call the foreign monad. So it's this way we kind of assimilate the foreign monad, arbitrary foreign monads into the base. So we adapt the base in some way to an arbitrary foreign monad. So this code will be written once for every base monad. And then the result is the combination of two monads. So as long as we can write that code for every monad, L, for every base monad, we are fine combining any monads. Now, this then illustrates how to combine list with try. And using the transformer, you can do the same thing. The code will then look like this. So you just combine list with try, and you get code that compiles and works. So the notation that I use for transformers looks like this. There are several notations that I use, but one of them is the T, where the base monad is in the subscript the foreign monad is in a superscript, and then there's still a type parameter A, which is also in a superscript. So M and A are type parameters of this type constructor, but this trimonad, for example, and more generally the L monad, so more generally you would have TLM like here. So the L monad is not a type parameter of T. And that's why it's written as a subscript. Type parameters in my notation are always written as superscripts, and subscripts are not type parameters. So for each L, it's a completely different TL that you need. So this is similar to notation such as T1, T2, T3. You use a subscript to indicate some kind of similarity between these things, but T1 and T2 could be completely different. They don't have to be similar in any way. So one is not an argument of the function T here. So that's kind of a standard mathematical notation that I use also for monad transformers. So then I show how to define monad transformers for a number of standard monads. Reader, either, writer, and so on. So these formulas might be difficult to read if you're not familiar with this notation. This notation is very close, however, to Scala code. It can be translated very easily into Scala code. The only thing that is maybe not very easy to get used to is the superscript, which is type parameter. In Scala, this will be square brackets. So for example, this one is the unit type. So this is a function from unit to M of A. So in Scala syntax, this will be like this. The plus is the co-product or disjunction. So this will be either A and unit M of A. And then M is outside, and this is the type parameter of M. So this is the Scala syntax for this. And I do give Scala code for all of those constructions. Well, some at least. Writer, list, transformer, and so on. State, continuation. Yeah, so here's the eval transformer. This is what I was just writing. This is this formula. So I show how to implement them. Then the question is, what if I have more than 2 monads? I have 3 or 4 or more monads. How do I combine all of them? How could I do this? This is not very trivial, and this takes a bit of work. But actually, what you can do is you can make a so-called stack of monads, where you use the first one transformer. Let's say you get TLM, that is a new monad, and you use that as a foreign monad for another transformer, like TK. And so the result is this construction, which is called a stack of monads. This is here's an example of stack of monads. It is just a composition of transformers, but then there are these stars which are necessary to convert type constructors into type functions. So this is not very easy to read, but that is what you have to do. So in my notation, it looks like this. So this would be reader, So transformer, so I say T reader, and then T writer state. And then comma A. So this A is the last type parameter, which is on the outer transformer. So these do not have a comma A because this needs to be understood as a monad, as a type constructor. And that's why I have these stars here. So I show that sometimes the order of stacking does not matter, and sometimes it matters. So in general, it's not the same. So sometimes it's not the same, but sometimes it's the same. So this is kind of difficult. This is not easy to guess. We have to check whether it's the same. You have to check what is the transformer that you need. You can stack monads in different order. The result will be different kind of effect. And I show an example here, which is combining either with state. And the result is that one of these monads shows that there's a state that sometimes is not updated because sometimes there's an error. So there's an error preventing a new state from being computed in the state monad. But in the other monad, new state is always computed. The error only prevents the result of type A from being computed. And so this monad looks like the either monad could cancel the state updating effect of the state monad. But in this monad, it cannot cancel it. And so depending on what you need in the application, you have to be careful in choosing the order of the monad stack. In many cases, it doesn't matter, but in some cases it matters, like in this one. In order to describe monad transformers more clearly, I introduced this notation. So this notation means the monad L is being transformed as a foreign monad by the base monad K. So, or if you wish, the base monad K is being adapted to the foreign monad L. The result of this is a monad, new monad, which is the same as what I defined, what I denoted by TKL. And what is interesting about this operation is that this operation is associative and has a unit or empty element. So this is a monoidal operation on monads. Associativity is by definition the monad transformer of a transformed monad is just a stack. So the stack is associative by definition. We do not define the monad transformer of this monad in a different way. We always define it like this. And so we can write a stack without parentheses. It is much easier sometimes to reason about stacks if you write them in this notation. And I give examples, and I show that the identity laws hold. So the identity monad, which is just the identity functor, serves as the empty element for this operation. So it's like a unit element or empty element, whatever you want to call it. And that is very interesting because that means monads could be combined sometimes if you have the transformer. So all monads that have a transformer can be combined using this operation. And then it's a monoidal operation. It satisfies associativity and identity laws. So associativity law allows us to write the monad stack without worrying in which order we stack. First we stack this or we stack that. Now the order K, L, M, N overall must be fixed. It's not the same as N, M, L, K, but the parentheses here are not necessary. So now this can be formalized what is necessary in the type class for monad transformer in order to be able to combine two monads in a big monad. You need to define the type, which is T. And so this type T will be the monad transformer if certain methods are available for it. And so one method is the new monad must be a lawful monad. It must satisfy the laws. Then there is lifting, and there are two lift functions, the foreign lift and the base lift. The foreign lift lifts the foreign monad into the big monad, and the base lift lifts the base monad into the foreign monad. And here the base monad is fixed. It's some fixed type constructor. So this is not a type parameter of T. It can be or must be perhaps a type parameter of M trans. I will take a look at this and see how best to organize this code. But right now I'm just treating this as a fixed type parameter. So for each base monad, I will define a new type class maybe. But this is up to the library designer. So when the library designer implements this, then they have to choose how to figure this out. I'm more interested in the required laws and properties, and then I'm less interested in how to design the best monad transformer library. So the foreign lift and the base lift must be available. And then there is another method which is called foreign run, which allows you to transform one foreign monad into another inside the transformer. So this is an interesting method, which actually is not available for all monad transformers. It is often available, but not always. And this method means that when you have a monad morphism between monads M and N, you can lift that monad morphism. So this is something I call the runner, because often this monad is much more complicated than this one. This could be just some either monad or trie in Scala. And this could be a complicated monad with side effects. So when you run that, you get final results. So that's often called a runner. And this runner is lifted to a runner on the transformed monads. So if you have all these functions, then you're completely free to combine any monads with the base monad, and you are not restricted in what you can do. You can run the resulting stack, as I show in the next section. You can compose any number of monadic computations with whatever monads, partial stacks or complete stacks that you have inside this one stack. So you can lift anything to the big stack with no problem, as long as you have all these methods: lift, run, and base lift is defined through a run. So then I show how you can define these lifts for a stack. So how you lift, for example, this monad, which is part of this stack, to the full stack monad. This is not so difficult, but it is cumbersome. There's a lot of detail here, and each of these lifts are different. So the code that would use that kind of technology would look like this. So you lift, and then you have to specify what you lift to what with type parameters, because type parameters cannot be inferred here. The Scala does not know to what type to lift here. And so this is very inconvenient. If you change anything in the stack, if you need one more monad in here, KLPMN, say, then all of this will stop working, and you would have to rewrite, carefully changing all of these things, adding more lifts, adding more type parameters. This is very inconvenient. And so for this reason, there are techniques where the lift functions are automatic. And I show two such techniques. One of them is more easy, and the other more difficult. So the easier one is lift relation. So lift relation means that you can lift from monad P to Q. And so that could be described as a type class. There is a monad morphism between P and Q. And then you can just define lift relation recursively using Scala's implicit mechanism. And this will extend the type class to more monads. So you, for example, initially you have liftings from L to the stack LM, and from M to the stack LM. And then from this, you can derive liftings, say, of this kind. If you have a lift L to K, then you derive a lift L to K transforms M. And so on. And so I show how this works, and I give a code example where I can create a value of the monad stack by just using the automatic lifts. All I need is to have some number of type class instances. The number of type class instances is linear in the number of supported monad types, so this is not so bad. It is much better than having to write custom code for each pair of monads for lifting. And then you can write code like this. So this is one solution, which is automatic lifting. Of course, this needs to be implemented in the library. It will be very hard to require for programmers to write this kind of thing every time. So it should be defined in the library, and then you should be able to use it. And the second approach is called the MTL style approach, or monad transformer library style. Now, this is a specific style which is quite different, because it chooses a set of standard monads to which this approach will apply. And for all of these monads, it defines specific operations that these monads provide. Now, the concept of operations has not been used so far when we discussed monads. And so it's not clear what those operations must be. In a specific example, you have some operations that people think are appropriate, but there is no definition of what those operations should be. So as an example, the reader monad has one operation called get. And this operation, or read, or something like this. And this operation is just a value of type R2R. It's an identity function. But so the state monad has two operations, get and set. And these are specific values of certain type. So for example, get is a value of this type, and set is a value of this type. So the idea is that you should not write code directly using the monad and constructing a value of this type or a value of this type. Instead, you should be only using operations. And then you can rewrite your code instead of using a specific monad like state to writing code using a type class. So you define type classes for each monad. For reader, you define a type class reader monad operations. For state, you define state monad operations. It's a type class that says the type constructor maybe has some reader monad inside somewhere in the monad stack. So it's a big monad stack, but you don't know which one. It has the reader operation, which is lifted already for you in some way. But you don't have to know how. You just use the operations. So the result is that you write code like this first, and then you replace S, a specific type constructor, a state SA, by an arbitrary type constructor that has the type class instance. So you don't actually know what type program you have, but you know that there is a state monad ops instance on F. And then once you do that, you can get the same code with no lifting necessary, because the lifting is contained inside that type class instance. And so you don't know how to lift and you don't care. This is the type class, which gives you get and set. And you're not supposed to use the state monad directly like this. Now, this is a definition of state monad ops for the state monad, where of course you have to use explicitly this type. But this is only in the type class instance. In your code, you're not supposed to do it. So your code must be rewritten so that it does not use the information about specific types of monads, like for example, state, like this, the state. Your code should not directly construct values of this type or directly apply values of this type to argument S and so on. So your code should only use get and set. And then you can rewrite your code in MTL style. So all monadic code must be refactored so you will have reader, writer, state, and other monads that you use, list, and so on, via type classes. So the library should provide all those type classes. And then the library provides liftings automatically. So you don't have to write liftings. And then I show how this works. There are some problems with the MTL style. Now, these problems certainly are not very, very severe, but it's very complicated if you want to solve all of those problems. And one problem is that there are a lot of operations. If you want to add a new monad, you don't know how to do that. What if your new monad is some custom data structure that you need for your business logic? You don't necessarily know what is the correct set of operations in advance. So for state, for example, get and set seems to be enough, but actually is not enough. Because sometimes you need atomic update. And atomic update is not the same as a sequence of get and set. You need now an update operation. Do I need some more operation? We don't know. So there's no principle or system that tells us which operations are enough. So for the reader monad, for example, people use the ask operation. But actually, there's another operation that people use, the local, which substitutes a different value of R only for one computation. Do you need that? Yes, maybe. But so do you need other ones? For either, there are several operations that are not trivial. Maybe not clear what else you might need. List. You want a filter operation. You want some other operations on list. Maybe flat map you want on list. Well, do you want map, flat map? Well, that doesn't seem to be necessary, but what else do you want? Append, distinct. Anyway, so this is the problem that there's no system to this. Writer, a very simple monad, it has 4 operations listed in this table. Are there more operations that I need? We don't know. The continuation monad has these operations, which are not easy to understand. And so if you add a new operation, you need to update all type classes to add this operation and to be able to lift it to arbitrary monad stacks. So that is a lot of work, and you cannot do that as a user of the library. So the maintainers of MTL style library have to decide which operations are supported, and it will be hard to support a new operation. The second problem is that actually we don't always know how to support new operations. Lifting these operations cannot be done in a systematic way. Sometimes it is easy, sometimes it is not easy, and sometimes nobody knows how to do it. And so the maintainers of the MTL style libraries have to make a choice of what operations they know how to implement and they want to support. And the third problem is that MTL libraries are large because you have to have a quadratic amount of code in the number of supported operations. This is the practical side of monad transformers that make them actually complicated to use. But sometimes, if you just have a few monads to combine, that could be a good approach. So if you have 2 monads that you want to combine, and certainly take a look at the table of monad transformers, implement your transformer. You can implement it in a few lines of code. It's very easy. If you just have a few monads to combine. So like I showed here, where is it? Here. So as I showed here, the standard monads have these transformers. It is relatively easy to implement these transformers by hand, and liftings are not so complicated to implement by hand. So using a big transforming library might not be necessary if you can just do it by hand in 10 lines of code. Just a comment about the ZEO library. The ZEO library takes the approach that you do not use any monad transformers. ZEO provides a big monad for you that has a lot of things inside. It combines reader, ether, future, and so on. So you do not actually use that library with monad transformers. And so there are reasons to do that. In most cases, you might not want to invest in the monad transformer library. In some cases, you might. So this concludes the practical use section of the book. And there is actually another section later in this chapter that shows proofs for the MTL style liftings. And it's quite technically challenging. I'm using the papers shown here, which are technically very difficult, but they are quite clearly written, and I was able to understand what's in them. In this section, I will show more of this theory, but right now I don't think it makes sense to go through it. So what are the laws? Well, they're very easy, actually, the laws. Most of them are laws of monad morphisms. You want to lift, I motivate Y, and those laws must be imposed. They're essentially laws of monad morphisms. You want to be able to run a monad stack in any order. So if you have a monad stack like this, K, L, transforms M, transforms N, then you might first want to run the effects of L. The result would be a stack like this. Then you run the effects of N, say. The result will be a stack like this. Then you want to run the effects of K. The result will be M. And then you want to run M, say, into the identity monad. And so you should be able to run in any order. You should be free to choose the order in which you evaluate effects. In principle, you can do that. In practice, many monad transformers are not compatible with this approach. They do not have the necessary runners. Prominent example is continuation monad and task-like monads, future and task and so on. Those monads do not usually have base runners, or they don't have transformers at all because they're not really functional code. There's some low-level code that cannot evaluate transformers. And so if you have these monads, then you cannot run effects in arbitrary order. But in principle, it is interesting to find conditions when you can. And so that is what I do here. I show how to do running even with an arbitrary target monad and what laws are necessary. And I find a number of laws, a large number of laws. Then I simplify these laws. Now, simplifying these laws is not easy. And I use some guidance from category theory in order to find out some kind of formulation of these laws. So I find monadic naturality, which is a generalization of naturality law, quite similar, except the function phi, which is here, must be a monad morphism. And so monadic naturality means that, for example, I lift monad M into a transformer. I can also transform first monad M into N and then lift, or I can first lift and then transform under the transformer, and the result must be the same. So this works only when this is a monad morphism, because the structure and methods of the monad must be mapped correctly to the structure and methods of this monad in order for this even to have a chance of working. And then I find that you can actually formulate all the laws of monad transformers in a single sentence. A monad transformer is a pointed and co-pointed endofunctor in the category of monads. Now you can remove co-pointed if you don't have or don't need runners. Without runners, it is just a pointed endofunctor in the category of monads. It is remarkable that this one sentence formulates all the laws of monad transformers. There are 18 of them. On the other hand, this sentence is too dense. It has too many things in it. It's not easy to use and to understand. So I would use this sentence more as a joke. A monad transformer is just a pointed endofunctor in the category of monads. What's the big deal? But there is actually a big deal. It's a lot of laws, a lot of technical details that you can go through if you want to. And here I summarize all these laws. I show examples where I fail to have a monad transformer because some of these laws are not satisfied. Finally, I give proofs that monad stacks actually work, that you can have a lawful monad stack by stacking lawful transformers. So this is an important proof that gives us assurance that our techniques of monad transformers are reasonable. When we stack monad transformers, we get still a lawful monad transformer. And then I prove this for 2, and then I prove this for any number of stacked monads, which is actually easier than proving for 2. So this, I will stop here to reflect. Why would we be interested in the laws of transformers? It's because if we can write down some kind of combination of monad type constructors, we would like to know that we did it correctly. So for example, how do I combine list and try? I say list of try of A, or do I say try of list of A? Try and list are monads, so I want to use them in a functor block. And if I combine them incorrectly, my functor block will look correctly, but will not work in certain cases. And it will be a very hard situation. The bug will be pretty much impossible to find and to understand. It will sometimes miss certain data or repeat incorrectly certain data, but you would not understand why. And the reason why is that this is incorrect. Only the first one is correct. The combining of list with try by composition must be done in this way. The list monad transformer does not work by composition. The try monad transformer does. So if you combine list and try, you must combine either like this by functor composition, or you have to use the list T transformer, which is much more complicated. But this is wrong. And so the only way to see that this is wrong is to see that the laws do not hold. And so that's why it is important to check the laws. Now, that said, when an engineer writes code, it is not necessary for the engineer to write the proofs. As long as the engineer knows that this is correct, because it is written somewhere with proof and somebody has checked this proof. So it is important to have these proofs somewhere, and in principle, you could learn them. But it is not necessary to use these proofs or to write them or to check them while you're writing code. So you can have a table that shows you correct monad transformers. You just use that table. Or you use a library for monad transformers. Presumably people who maintain that library have checked that everything is correct. The important thing is that it is possible to check. There are laws which are formulated in this section. Where's this? Yeah, in this section, there are laws. You can check them. You can prove that they hold if you want to. So this is not an opinion that try of list of A is not a good monad. It's not an opinion. It's a fact that can be checked by derivation and mathematical proof. So I will stop here and I will continue in the next tutorial to go through the function composition-based transformers, which are these. So either foreign monad is outside, base monad is inside, or foreign monad is inside, base monad is outside. So in Scala syntax, this will be M of L of A, and this will be L of M of A.